Good afternoon, good evening, and good morning. Greetings from Stanford University, and welcome to the 27th AEC Global Teamwork Final Project Presentation Cyber event. My name is Renate Fruchter, founding director of the PBL Lab, and your host for the day. The PBL Lab is the home of the AEC Global Teamwork course I've been teaching since 1993 with partners worldwide. Our vision is to transform our students' tool set, skill set, and most importantly, mindset, moving from working in discipline silos to work as a single, cohesive, interdisciplinary team and develop fully integrated solutions. Our aim is to prepare the next generation leaders and change agents for the future workplace and challenges that they will encounter. What is unique about this class is that it brings together students, faculty, and industry mentors from 5 disciplines: architecture, structural and mechanical engineering, construction management, and life cycle financial management. Students learn to collaborate in globally distributed teams to virtually design university buildings, addressing local hazards such as earthquakes, hurricanes, flooding, local labor conditions. I have to say, this year has been a great pleasure to mentor and work with highly motivated, creative, and committed students from Stanford and 12 university partners worldwide. Given the unprecedented COVID-19 challenges and shelter in place, we are organizing this annual event in cyberspace rather than having everyone back at Stanford for a final great, engaging celebration. For this purpose, each global student project team prepared a video story of their project evolution. These stories are reviewed and assessed by about 30 industry mentors prior to the May 8th cyber event. But before we dive into very exciting student presentations, I want to extend a big thank you to our industry and faculty mentors, alumni, and owners and sponsors who so generously dedicated their time, attention, and knowledge to our AEC Global students. In collaboration with industry partners, we defined 3 challenges to further foster the students' creativity, focused on sustainability, specifically this year, resilience, integrating project delivery, focused on the question whether to industrialize or not to industrialize, as well as shared risk and reward, and technology innovation, focused on intelligent interoperability between models and disciplines. Winners will be announced at the end of the cyber event, May 8th. So don't forget to visit the PBL Lab Project Gallery website to find out who this year's winners are. Last but not least, a special thanks for the generous support of our technology industry partners that enable us to continue to develop new ways of working and learning by leveraging the latest emerging technologies like VR, virtual reality, AI, artificial intelligence, parametric modeling and optimization, and embed them in the students' new daily work practices that they experience in this global teamwork class. And with that, let's move on to the student presentation.
All right, hello everyone. We are Team Central, and we are happy to be back on screen today showing you our new engineering facility building for the University of California in Los Angeles. First, let's introduce the main actors. Our team consists of Madeline, Anders, Killian, Mo, Wenji, and myself, Thomas. And our owners are Vikash, Boris, Korish, Sohan, and of course our CEO and super owner, Renate. Starting with the set of our production. Our story takes place at the campus of UCLA in the heart of Los Angeles, California. Located in Southern California, the LA area has year-round hot and dry climate. Rainfall is scarce, with virtually none over the summer. Our site represents the southwestern entrance to the UCLA campus, surrounded by residential areas to the west, commercial areas to the south, and a hospital in the direct neighborhood to the east side. Further investigation shows the very gray concrete surroundings of the site, along with the very busy traffic characteristic of Los Angeles. Considering the site characteristics, a resilient design from the engineers was required to account for the challenges of a high seismic zone, the Santa Ana winds, and water shortages resulting from the hot and dry climate. A tight site, noise-sensitive neighborhood, and busy traffic patterns were obstacles for the construction managers to overcome. The urban concrete surroundings were seen actually as an opportunity to exploit by the architect, as the team aimed to produce an iconic building that stood out at our owner's requests. In the winter quarter, we developed two big ideas, the palm tree and the cradle, aiming to integrate disciplines, build sustainably, and meet the owner preferences. A combined team and owner voting resulted in choosing the cradle design with a timber structure, which scored high in environmental sustainability and architectural design.
Time to get excited for the cradle. The chosen concept addresses one of the biggest challenges of our present and the future. Massive amounts of waste produced by excessive consumption and linear material use is resulting in unfavorable conditions for both planet and people and puts our future in danger. There's no choice but to reconsider our actions, big and small. And with this concept, we aim to contribute a bit to challenge linear thinking for the sake of humans and nature. Our big idea of the cradle is to design and plan a building that reconnects people and planet, focusing on the needs of users while moving from a linear material use to circular thinking, while ensuring that our building is prepared for the future and its challenges and offers an attractive learning environment at UCLA. This year's challenges has all helped us to further refine the big idea and adapt different perspectives to user well-being and circularity. Designing for resilience addresses both the building, the integration of the occupants, and the resource efficiency in circular construction to be prepared for future changes and challenges. We assessed how prefabrication could help us deliver a high-quality circular building and integrated different softwares and processes to back up our design choices with more informed and quicker decisions. With this said, welcome to the cradle. The cradle presents itself as an introverted building, blending in with the color scheme of the surroundings, while at the same time attracting public and students with its playful facade scheme. Being located at the edge of the campus, the building orientation and concept design was guided by the flow of people and the innate ability of the double dimension footprint to have a central meeting space. We wanted to create a welcoming meeting point both inside the building and outside, featuring a big atrium around and a green plaza around the building. The plaza is a much needed green area, contrasting the concrete surroundings of the area, placing the cradle in a welcoming, inviting setting. Upon entering the building, visitors and students find themselves in the big atrium on the ground floor, from where they can also access the auditorium and two big classrooms. The building truly opens up from the inside, creating a homely feeling for students, staff, and visitors, reminiscent of a small village. It inspires interaction and innovation through visual connectivity, forming a kind of internal village of different levels, and makes bold design statement with the cantilevered study spaces up on the upper floors. The atrium is designed for acquisition and approbation, inviting occupants to make the space their own with flexible furniture. It is also showcasing circularity in a very, very tangible way, using recycled or renewable materials such as newspaper wood or recycled windows on the cantilevers. Engaging the discussions about building performance and circular energy usage through an interactive smart wall is also part of the atrium. The smart wall informs users of our current resource consumption and in the building and the latest circularity research findings. The second biggest entity next to the atrium is the auditorium, spanning 2 floors, since the aim of circularity demanded as little concrete usage as possible. The backside of the auditorium on the first floor can be separated by a moving wall, allowing a flexible use of the space, whether it will be part of the auditorium or as a classroom. The first floor in general accommodates learning spaces such as classrooms and seminar rooms. On the upper floors, we additionally understand the corridor as an opportunity to foster collaboration and exchange in the student body. We therefore include breakout spaces that look into the atrium, not only providing visual connectivity throughout the building, but also a stellar view into the iconic atrium. On the second floor, we accommodate more faculty body and staff, providing a more work-like ambience and a more quiet ambience. Here also the breakout spaces underneath the skylight form an interesting play with the corridors and niches for interaction and collaboration. With its concept, the cradle is truly welcoming, providing learning and workspaces for all different kinds of personalities. Whether a student or staff member feels more comfortable in a personal interaction with others or needs quiet learning spaces, any option can be found in the building. Beyond the learning spaces, the building engages the occupants to contribute more to circular thinking. For example, by participating in a workshop in a repair room on the ground floor or an interactive playful waste collection system on the site. Overall, the architectural design provides different spaces for optimal learning and working experience realized in a resource-efficient way with innovative materials.
Now on to the structure of the cradle. Together with the architectural vision, the seismic activities in the LA area were the key drivers of our structural system design. Using ASCE 716 and USGS, site parameters were investigated and it was determined that the seismic design category is category D. With these determinations, we were able to define the design response spectrum as shown on the slide. Engineered timber was selected as the main structural material to achieve goals of sustainability for its low embodied carbon and prefabricability for its lightweight properties. The framing system for gravity loads consists of CLT panels supported by glulam beams and columns, which transfer the load to a reinforced concrete substructure. The lateral resisting system consists of CLT rocking walls, a resilient design which will be explained in detail later. For support of the cantilevered areas, steel timber trusses systems were selected. Using the determined design live loads, dilutable RFEM was used to design and check cross-section capacity of both timber and steel members. Looking at the framing plan, the building's substructure consists of a 6-inch concrete slab on grade with isolated footings. For the first floor, the framing consists of glulam columns and girders following a regular 19-foot by 19-foot grid with intermediate glulam beams mid-span the girders. The second floor follows the same grid and arrangement, however with deeper and wider girders above the auditorium to accommodate the longer span. The framing of the roof consists of thinner beams of less depth to optimize material use, since live loads do not apply to this level as they do on the first and second floor. RFEM was used to verify the cross-section capacity of the steel truss supports and the serviceability of the cantilevered areas. Using HSS 8x8x3/8 steel members for the truss, we were able to achieve an impressive acceptable maximum deflection of about half that of the allowable. To support easy disassembly without compromising structural integrity, we opted for bolted connections rather than welded for both steel and steel timber connections within the cantilevers.
Cross-section capacity and serviceability were verified for all timber members. Diagonal supports were added in the auditorium to decrease beam depth, ensuring views from the back rows were not obstructed. Following the idea behind cantilever connections, typical connections between different elements were chosen to be easily assembled and disassembled to support the circularity and cradle-to-cradle concept behind the design. To ensure the safety of the building during earthquake events, a TAPS was used to define all the relative seismic parameters considering both the design basis and maximum considered earthquake. For the latter resisting system, we are proposing an innovative system which is CLT roofing walls with chronocular fuses. The system consists of CLT shear walls secured to the foundation with post-tension cables. The walls are connected to frames with chronocular butterfly fuses, which allow the location of the plastic hinges and points of damage to be predicted and controlled. The formation is limited to the fuses rather than the frame, which can be easily replaced after a seismic event. Chronocular fuses support resilience in our structure design, as they can be explained in three major features, which are deformation control, easy replaceability after damage, and simple fabrication. Its mentioned features help in limiting the extent of damage, preventing building closure, and consequently reducing the cost of repair. These benefits all support the idea of resilience. In terms of performance-based engineering, roofing walls with chronocular fuses were tested in ETAPS nonlinear analysis through a simplified beam truss model. Testing for a design-based earthquake, immediate occupancy criteria was met, meaning the building would not require closure after such an event. Testing for maximum considered earthquake collapse prevention criteria was readily met, ensuring the safety of occupants in such an event. And revisiting the big ideas behind the concept, earthquake resilient design ensures user well-being at any time. Timber materials and bolted connections designed for disassembly support circularity.
From the MEP perspective, we looked into making the energy and water supply more circular and design an efficient, adaptable ventilation system that reduces energy consumption while also increasing user control and well-being. The energy for the building will be produced by solar panels on the roof and skylights. The cradle works as a microgrid concept with large flow batteries that can provide power when there is no production of the PV panels. It also allows for maintaining electricity for essential needs of the building for an entire week in case of an electricity failure. As a backup, the microgrid is connected to the UCLA grid. The cradle will be ventilated through an underfloor air vent distribution system. This system allows for more ceiling space, creating a stratification layer for latent air. By using individually adjustable floor dampers, building occupants also have more control over the local thermal environment, while still maintaining a high efficiency of the system. The interior walls are built on top of the raised floors, allowing for floor plans to be more flexible for future reconfigurations. This schedule shows the different climate zones and having different load factors. The ventilation system meets each zone's requirements while also optimizing the overall energy consumption of the building. This means the cooling load is determined at 230 kilowatt, which can be supplied by 2 separate air handling units on the roof. The MEP and electric utilities rooms are located at the ground floor level in the northeast and southeast corners. The atrium and classrooms are ventilated actively along the building envelope and passively by dampers in the center. On the second floor, the underfloor supply is ducted with outlet dampers into each classroom and meeting room to enable local control where needed. The perimeter is conditioned by convection units. On the third floor, the supply plenum is not subdivided and it has a constant low air pressure throughout the underfloor. The supply air into the perimeter offices is controlled by the convection terminal units, which can cool and heat air locally as desired by office occupants. Hybrid ventilation. The architectural design allows for the implementation of hybrid ventilation to reduce the use of the mechanical ventilation. The large cantilevers create a cool and pleasant climate that enables a passive cooling of air before it enters the building. The cool air will create a stack effect, pushing latent hot air up towards the large open atrium skylights. On the third floor, natural cross ventilation is also possible through the extended hallways out to the perimeter. with the use of a hybrid ventilation, we were able to lower the overall energy consumption enough to make the building the cradle and net zero building. Using Internet of Things sensors allows to not only monitor indoor thermal parameters, but also to predict future outdoor weather conditions in advance, like the Santa Ana winds. Based on these data, the VAC system will automatically select which ventilation will work best according to the optimal pollution. Prepared for disruption, not only in daily operations, but also in the case of unexpected events. The ventilation system can respond to different disruption scenarios. In case of failure of one air handling unit, the other one will get in and provide enough energy for the entire building. Should both fail, there's still separate convection units around the entire perimeter to support these zones with ventilation. In case of power outages, natural ventilation will still be available from window and skylight openings. To improve the general water consumption of the building and respond to increasing water scarcity in LA, the building includes 6 hydroloops to enable cleaning and recycling of gray water for purposes of toilet flushing and garden water. Essentially, this system lessens the burden of fresh water supply, which is otherwise a regional problem during ever-increasing drought periods. The service design hence enables both circular use of resources and energy, as well as a high degree of occupant control and a system that is able to respond to different scenarios.
The individual solutions were all guided by the pursuit of circularity and user well-being, but only the integration of different disciplines allowed us to truly take this ambition to the next level. A lot of team efforts were focused on the facade and the atrium, creating an inviting, iconic building from the inside and outside, and we will look into these considerations more in detail in the following. How do we propose an iconic facade solution? The design of the facade was characterized by several iterations to balance structural safety and architectural design. The construction managers also had a saying in the design process, pushing for high standardization to enable prefabrication and disassembly, a shorter construction process, and cost-efficient circular material choice. On top of that, an efficient, simple shading solution had to be found. Awnings from recycled sails is a material-effective shading solution. It is traditional, but allows for individual operation for each window to provide the desired daylight amount for each room. The awning solution was examined using Iris VR, and only a small amount of the low winter sunlight enters the southeast facing classroom at both 9 a.m. and 3 p.m. The result of these cross-disciplinary efforts were the 5 different facade patterns, which still make up a playful, interesting facade pattern, but at the same time enabling a learning curve for efficient installation as well as easy disassembly. The disassembly of the facade is further supported by the design of connection details that connect the panels to the structural frame using screws.
A big factor to determine the level of circularity was the facade material. Finally, we chose recycled aluminum, which has outstanding appearance, good thermal properties, and not too expensive. Having determined the layout of the panels, we evaluated the construction process. The biggest facade panels are about 20 feet long and 11 feet wide, since the most prevalent track width is under 12 feet. This is the heaviest architectural element. Thus, it determines our mobile crane capacity. Here is the just-in-time delivery and installation process for our facade panels. Here is the KPI diagram for facade panels installation, including truck unloading the panels to the material laydown area. The upper control limit is is 60 minutes, and the average installation time is 46 minutes. Thus, we can install 8 panels per day, and the facade installation will take 3 days per floor. Overall, the facade plays a key role in achieving our big idea implementation.
The focus of discussions was the atrium, our key design feature on the inside. Creating and inviting meeting space for occupants and visitors in and around the atrium is a central part of the user well-being goal. Realizing the architectural design has particularly affected 2 areas: skylight design driven by the MEP, SE engineers, and the construction of the cantilever learning space on the support floors driven by the construction managers. The initial skylight design following the standardized grid wasn't very pleasing from a design perspective, and also resulted in a lot of areas with insufficient daylight on the upper floor. Calculating a skylight support structure put above on top of the rest of the roof frame enables the skylight to be placed centrally in the atrium to wrap around the boxes into the breakout zones. This provides twice the amount of daylighting for the interior boxes and hallway spaces.
Madeline, I believe you're muted.
Sorry. To bring the atrium to life, the construction strategy also had to be evaluated, with a particular focus on the cantilevered spaces. While the owners are mostly interested in getting a high-quality building on time and budget, the construction managers saw a number of risks and challenges that need to be mitigated to achieve these goals. In order to get a better understanding and an overview of the potential risks, we created a risk matrix with the team, brainstorming questions such as what can happen, when can it happen, and why? Who is going to be affected and for whom is it a risk? And then for several building parts like the facade and the atrium cantilevers, we looked into how prefabrication could help us handle the risks in order to avoid safety and logistics issues and save cost and time. For the atrium cantilevers, we looked into 3 different solutions: traditional assembly, prefab panels, and prefab boxes. There are several logistics and safety risks related to this construction process, affecting a range of stakeholders that all share an interest in mitigating them. Looking into safety first, the goal here is to avoid injuries, heavy lifts, and defective work. We evaluated the work steps that need to be performed on site and the component dimensions. While the traditional assembly poses the highest risk in terms of injury and defective work, the prefab boxes are rather heavy and big elements that need to be lifted, and in addition require a larger truck that will come with additional costs and transport safety implications. From the safety perspective, the panels hence seem to be the preferred option. Going deeper into logistics risk, we also wondered how the sequencing and installation time would affect the risks of delay and spatial conflicts. While single elements and panels can be installed during interior works in parallel with other tasks, prefab boxes will need to be installed during the structural erections. Using prefab panels allows us to better use the crews on site and reduces the risk of schedule impacts in case of material delivery or construction delays. But what are the rewards of the different solutions in terms of time, schedule, and quality? Using different models and alloys to assess the options, it is suggested that the prefab boxes will be the most time and cost-efficient solutions. However, installing them during the structural sequence leaves them the sensitive newspaper wood cladding that we chose exposed to pollution and sun. Therefore, to ensure high quality without changing materials, it seems not advisable to opt for the prefab box solution. We decided to choose prefab panels and instead looked into how we could improve the baseline schedule that we use for comparison. Adjusting the crew sizes in the interior work sequence, we were able to shorten the estimated construction time by 13 days while simultaneously reducing the costs. With these collaborative effects, the atrium makes up a true center of user well-being and circularity in the cradle as well.
Then, how can we construct this truly iconic building safely and efficiently? Our answer is always safety first. Our construction planning was guided by safety considerations to provide a safe workspace without disrupting the public. We used the risk matrix mentioned earlier to design a safety concept, addressing both the daily safety measures on site as well as the responses to emergencies and challenges such as COVID-19 pandemic. Planning the site logistics, our main entrance and exit for heavy transport is on the west side to avoid the noise impact on the hospital to the east. In addition, we'll use noise blocking wall as our temporary fencing. Since our site is very tight, we'll rent additional site offices across the street and use the visitor parking lot to the north side. In response to the COVID-19 crisis, we placed a hand washing station along with a side trailer and toilet on the east side. During the excavation phase, the electric excavator and dump truck will place here, and the excavation process will take a week. For the concrete footings and slab on grade, we use Putmeister 28Z type concrete pump. According to the capacity of it, we expect to finish the substructure part in 40 days, including curing for the concrete. Our heaviest architectural element is the prefab facade panels, which weigh 27,000 pounds. As a function of the heaviest and furthest lift, we pick a mobile crane, whose radius is 130 feet. During the substructure erection, it will have 2 locations. Here is an animation of how our building will get constructed. The use of constructability visualization guided our design process and make our team decisions more sound and efficient. As for the construction time, our baseline schedule in Microsoft project has a total duration of 253 workdays, lasting from September the 30th, 2024 to September the 17th, 2025. But after exploring different scheduling options and the impact of prefabrication alleys, we are able to shorten the project duration to 225 workdays, finished on August the 8th, 2025. For the economic aspect, our design justifies a 20% budget increase from the owners. After putting the initial $40 million into a 5-year deposit in UCLA foundations, we can have an annual return of 3%. So our overall target is $15.2 million. The first chart is our target distribution for different assemblies after combining the data from RSMeans historical database and our owners' preferences. The second one is the actual cost distribution. There are major increases in services and special construction assemblies, whereas decreased portions in substructure and shell. The primary cost drivers are underfloor ventilation system, which is over twice of the price of the traditional overhead HVAC system, and the highly customized skylights, whose unit price is $300 per square foot. In a nutshell, our overall cost is within the budget and is about $475 per square foot. Our cost has evolved several times since winter presentation, and we track them using data scripts and RSMeans database. This allows us to balance aesthetics, user experience, and cost efficiency. Lastly, for our material procurement, we focus on national suppliers but we also try to trace the origin of key raw materials or components, like timber for structure and aluminum for facade. This allows us to anticipate potential delays quickly and react accordingly to ensure a timely construction for our cradle.
Let's look into the summary and statistics of our overall implementation of the big idea. Taking a step back and summarizing all the presented solutions, the cradle as a building reflects a clear focus on circularity and on user design. This is also supported by the assessment that we did of the building using the WELL rating for user well-being and tracking the circularity of the design choices. By continuously assessing the building performance through indicators of the user well-being from the WELL certification standard, it was possible to make sure that the cradle achieves the best performance possible for user-oriented design solutions. To this assessment, we achieved 80 points, which qualifies the cradle for the WELL Platinum rating. To achieve the goal of high circularity, we investigated a lot of materials, of which some were shown during this presentation. Tracking the design evolution directly from Revit, linked to one-click LCA, allowed us to identify the most significant material choices affecting our designs. This provided a detailed and comprehensive solution to engage the whole team in circularity discussions in multiple iterations. So that today we can present the cradle as a building that, by engaging all disciplines across architecture, structural engineering, MEP, and construction management, successfully combines circularity and user well-being in the new UCLA engineering faculty.
And now, ladies and gentlemen, it is time for the Oscar shortlists, highlighting the key points of how we addressed this year's challenges, resilience, shared risk and rewards, and in industrialization, as well as intelligent interoperability. Let me present. Designing for resilience addresses the building, the occupants, as well as the resource efficiency in circular construction. In order to thrive in the face of the unexpected and even extreme situations, like earthquakes and power outages, we use rocking walls and energy storage while maximizing the amount of circular building materials. We also keep in mind that encouraging the building occupants for innovative thinking is a key part of being ready and efficient. Thus, our building has functional spaces such as an atrium and repair workshops to engage them.
To make suitable prefabrication choices, we use the risk matrix to brainstorm likely risks in planning, construction, and occupancy with the team and describe their probability, impact, and consequences for different parties. In order to reduce the risks we found, we then evaluated whether different prefabrication options would allow us to better handle safety and logistics challenges using Alice Infuser. In the second step, we looked into the impact of prefabrication options on cost, construction time, and most importantly, of course, the quality that we deliver to the users and owners. Hence, combining human experience and artificial intelligence, we were able to identify a suitable construction strategy for, as shown for the facade and the atrium, that balances these interests and also created a basis for understanding and managing the project risks among stakeholders in different project phases.
We integrated different softwares and processes to support our design choices with more informed and quicker decisions for process, product, and organization. Linking the Revit model to one-click LCA allowed us to achieve a 44% increase on circularity by tracking the use of recyclable materials. These, to a large extent, guided our design iterations. Visualizing the constructability infuser and validating the baseline schedule in Alice, we better informed the designers from the very beginning. For example, we determined the dimensions of components that can be safely delivered and installed. Also, Alice helped us to identify optimal construction sequences, which resulted in a time saving of 28 workdays. By directly extracting quantity data from Revit using DynamoScript, The time used on cost estimates got saved for 30%. As far as the team organization, we conducted team evaluations every week and used the analyzed statistics to inform the team and owners and address our collaboration inefficiencies.
So let's look behind the curtain to see what led to the creation of this masterpiece. We will now share some insights into the collaboration of the last 4.5 months in Team Central. To overcome discipline silos and time zones and bring our building to life, we established a variety of structures and practices for our teamwork. We use different IT tools to support the collaboration, coordination, and communication among team members and with the owners. In the spring quarter, dedicated discipline days, as well as the increased team-wide use of Slack and Asana, helped us to improve transparency, response time, and feedback significantly. The analysis of our weekly team survey confirmed that very positive impact of the strategies. Overall, a typical week looked like this. We met in different contexts using Zoom and VR, and had a clearly structured week with discipline days and daily sub-meetings, as well as the weekly team meetings on Sundays. We use VR for different scenarios to enhance our experience and understanding of the design and planning across all disciplines. In sessions of on average 30 to 45 minutes, it helped us to get a better spatial understanding, immediate feedback, and also created a joint experience. Overall, the project offered us a tremendous learning experience that we love to embrace during the last couple of months. Long working hours, countless iterations, and sleepless nights were one part of the journey. But we had a great time in Team Central, hosting digital concerts, sharing Michelin-star dinner recipes, and playing mini golf in VR. We're really grateful for the opportunity to be part of this course, and want to thank first of all Renate, but also our owners and the many mentors that accompanied our journey, shared their knowledge with us, and guided our work. Thank you.
Thank you.
Thank you.